over a couple things about this course, which is not really a course, so that's why I need to tell you about it. So like a lot of other 6101 sections in NUS, these are meant as lab rotations for first-year PhD students, just for you guys to get a try about what things are like in a particular research area. I've chosen not to do that, so I'm just running basically what other people have taught before on the web, but as a chance for us to coalesce a whole group of very smart students together to learn a topic and also to make it available to the outside world. So that's why we have some guests here who are probably still from NUS, but probably not from SOC. And that's great. We welcome all of you to come. Okay, so I think maybe what we can do just very, very quickly, because otherwise it'll take the whole hour, is to go around the room, just say your name and where you're from, and whether you're a first-year PhD student in SOC.
My name is Jiang Kan. I'm from SOC, first-year PhD student.
Okay, welcome.
I don't see the link on the slide.
Oh, it's not on Slack. Okay. All right, thanks, Jeffro. Let me put the link there. I thought I had that. It's this one here. You can't see that, obviously. It's this one here. So, let's see. So, yeah, if you go to this link, bit.ly 6101-Fast.AI-1, you should end up in the Google Hangout, which is displaying this screen, albeit with a little bit of time lag. So I hope that works. If it doesn't work, let me know. It should work. Okay. Is it working? Anyone able to see it? Okay. If the audio is not working, you let me know too. Okay, so I'm just recording it just for posterity, not because we're conceited or anything, but just in case you guys are not able to be around, then it's a good chance for you to check the archives in case you've missed something. So this is run as flipped classroom, which means every week you guys in class will need to actually watch the videos from Fast.AI before coming to class. Okay, try out those actual exercises, and then you can come in, and then after that we come in and actually discuss it here. So I think Jiang Kang introduced himself. Let's go around the table first before going to the back. So, sir.
My name is Sylvain.
Sylvain.
I come from France, from electrical engineering, and I'm first year PhD in SOC.
Okay, welcome.
Hi, I'm Yami. I'm a first year PhD student in this group.
Hi guys, I'm Lula from Sri Lanka. I'm also a first year PhD student.
Hi, my name is Wang Ruiwei. I'm from China. I'm the first year PhD.
Hello everybody, I'm Yu Chen, second year computer science undergraduate student. I'm Eugene from SOC, first year undergrad.
I'm Jetro, second year SOC.
I'm Yongle, second year SOC undergraduate.
I'm Radhika. I'm a research assistant with Wayne.
I'm Nichon from China and first year PhD student in SOC.
Okay, and then
I'm Venu. I'm from India. I'm a visitor here. I'm my fifth year of undergrad.
Hi, my name is Shen Hong. I'm a research assistant in Providence.
Hi everyone, I'm Lee from Vietnam. I'm studying master in software engineering.
Welcome.
My name is Bala. I'm from ISS, associate lecturer.
Okay, welcome.
I'm Davis. I did my computer science in UT like 34 years ago. I'm in the enterprise. I'm in manufacturing in China. So I'm just
sitting in. Great. It's okay. Do you want to introduce yourself for a second?
Oh, okay. I'm Joel. Yeah, I've been here for the past 2 iterations of 3.1 and here again. Yeah.
Thanks, Joel. Okay, so as I was saying, this is not your typical course. We are basically just a study group for a course that already exists. The course has already been run. a course that has over 10,000 graduates. So the only hope that we have is to pull all of us together to study the lectures together, go through it. So the way it works is that it's basically we are going to run the first session with the PhD students. I understand there are about 6 of you here that are first year PhD students. For the second half, there are no PhD selected for this, so you guys are of course free to go on to your second lab rotation, but we'd very much like it if you continue on with the syllabus, even though maybe you decide not to come, okay? And so what will happen is basically this. What we need to do is 2 things. We are going to use this worksheet, which is also mentioned on Slack. It's here, this one here, 6101-lecture choice. If you access that URL, you'll find yourself at the sheet, okay? And then what I need you to do is put your name down, okay? Let's say my name is Kan Min Yen, so I just use my handle. You put your affiliation, and then say which sessions you're coming to. The first week, the first set of lectures, which is from week 3, which is today, to week 7, which is I think 5 weeks or 6 weeks away. Okay, or section 2. I think all the first year PhD students are in session 1, or both. If you can't come in person, then you would select neither. Okay, and the key thing that we need you to do is nominate yourself for 2 weeks of duties for the class. That means you will be presenting in class with the fellow classmates who have nominated that week. I will do some arbitrage, because usually what PhD students say is I will pick either the next week because I'm not busy, or the very last week because I want to postpone it all the way to the end. And so we end up with nobody in the middle who actually wants to do any work. Okay, so that's no good. We want to space it out so that we have presenters and moderators for the whole session. Okay, so I will do some rearrangement later of that. But what will happen basically is that there will be certain people allocated, as it says here, to a presentation role. Okay, that means you guys are going to lead the class, all right, and discuss things that came up in Jeremy's and Rachel's lecture. Okay, and there'll be people who are managing the Slack group. Okay, so right now we have our Slack group, and I hope you guys will use it to ask questions, especially those of you who are watching online who are not physically here. Okay, so raise them on Slack, and then there has to be somebody on Slack to watch. Otherwise, what we're going to do is we're just going to stare at the screen and no one knows what's going on Slack, and then the people who are participating online don't feel left out, right? So that's no good. Okay, so if you're in the classroom, please log into this worksheet. If you are outside, please log into this worksheet and then nominate yourselves for specific weeks. So the weeks are here. Sorry, this is the wrong URL. It should be this one. Oops. So if you go to the 6101 lecture page, yeah, basically all of the ones here, you can just pick a week. So this is week 3, week 4, week 5, week recess, all the way through week 13. Those are the topics that are here. So I've listed the topics and the video links to YouTube on the page. And so what you're responsible for is everyone in the class has to watch the lectures, probably version 2 of the lectures, at least a couple days before class. And later on in this class, we can actually set down a time that everyone can watch together if you want. And then, if you were all watching simultaneously, the Slack channel can be helpful, because then, we'll be talking about the same problems at the same time. Okay. And PhD students tend to be very late owls, so maybe that will be like 1 a.m. in the morning or whatever that everyone wants to watch on Thursday night, because Friday morning is the lecture, right? Okay, so we'll decide that later. Okay, but basically you'll need to watch these particular videos and then raise questions as the presenter. You're going to go through the material, and as the person looking over Slack, a moderator of Slack is to introduce links and discussions. So for example, if somebody, there's a seat up here if you want. Yeah. if the participation, the presenter is saying, oh, there's this nice archive paper, whatever, then the person who's doing the Slack moderation should find that paper and put it up on Slack. Okay, so everyone can benefit. It shouldn't be the presenter's job to do double teaming, right? Because it's a lot of pretty difficult to present while posting information. So that's why we have two roles in this class. One person to manage the Slack. It could be a team of people if we have a lot of people deciding, okay, or a team of people doing the presentation. Any questions so far? Okay, so the Fast.AI course is not meant to be theoretical at all. If you've read the description or you've watched any of the videos, it's very practical. They don't give you practically any math. It's all the terms are glossed over. It's just to get you started on the deep learning aspect if you haven't had it. If you've had it before, it will seem like a no-brainer to you because it's already all done. So you may want to, in fact, go to more theoretically inclined resources if you find those things a little bit too obvious or dry. So in fact, Joel and I think Jeffro and a couple other people in this room have been in past iterations offered by my lab group. We had one iteration on vision from the Stanford group, another iteration on NLP also from the Stanford group, and those are good places to find good links because they mention other materials. So I think their lectures, yeah, some of those lectures are on YouTube too, I think. Yeah. Any questions so far? No? So we're going to use this setup throughout all 13 weeks where we're actually live casting what we have here on YouTube on Google Hangouts. So then you'll have to get used to hearing the sound of your voice. Probably not your mugshot because we'll turn off and just use the screen share so that we can have it archived and saved for other people to watch. Okay. All right. One last thing that I want to bring up is that, okay, two things actually. In our schedule, this week we're going over the recognition of dogs and cats and the convolutional neural networks. We have 2 weeks from now, February 16th would be the normal class day, but that's first day of CNY, and CNY is a major public holiday in Singapore. So we're going to reschedule it to the 12th. So that means between week 4 and week 5 is only 3 days. So just be aware of that. So if you're available, great, then come to the lecture, which venue, which will be announced later. Okay, otherwise, again, you can watch it online or wherever you are.
What time will it be?
It will likely be 10 to 11 again. Okay, I need to double check on that. That's a great question. Thank you. Okay. Okay. Starting week 8, that's the second half of the course, which is actually a separate Fast.AI course. It's their second one. They'll be going over for things other than supervised machine learning in the traditional sense. Okay. So you're welcome to join that. One thing that will be required of all students in this course is participation in steps. Okay, so I've written it down here. All of you will be required to do a student project. Okay, and you're welcome to do it in teams. So it's much more fun if you do it with someone else. So I suggest that you can use the Slack group, in fact, to talk about it. So there's a projects link here, so you can say, "Hey, I've got interest in this Kaggle competition," or my work has some data set. I'm interested in doing classification or some regression on this. Does anyone want to help? And then you guys can come together and coalesce some project groups. I don't care what size the project groups are. Maybe from 1 to 4 people would be pretty adequate, as long as you are doing hands-on machine learning, because that is the goal of this course, is to make sure that you actually try to learn the machine learning models, not just to do the math. The math is great, but that I think plenty of SLC courses take care of the math. Okay, but here is actually just to do practical work and try your hands on something. Okay, so as a result of doing this project, you will also have to participate in this SOC Term Project Showcase. So for those of you who are first-year PhD students, you don't know this, but the undergraduates are pretty familiar with this, I think. Basically, every semester, at the end of the semester, there's this project showcase course, okay? Not course, evening. And basically what it is we take all of the courses that have a project component-based type of continuous assessment, and we have them all come together in SOC on the foyer on level 2. And we basically have a big night where people eat and talk about their projects and try to market their projects to win prizes from Google and other sponsors. Okay, and we've done this very successfully for a number of years. And last year we had some of these gentlemen here also participate in that. And in fact, if you rewind the Slack group enough, you'll see pictures from there. I think they're in the random parts or something like that. Yeah, so some of these are like, here's Jeffro, and there's Joel in the back. Okay, so they did their projects and we put them up on posters. The posters are printed by you but paid for by Google or sponsors. So then we have you guys all come down and present what's the latest and greatest thing in deep learning from you guys, you know, from a project perspective. Okay. So that's a really fun night that everyone gets to try out. Okay, and people actually do win some cash prizes, so it's not a terrible thing to do. Okay, so you need to put this on your timetable, 18th of April. So that is, let's see, March, April. 18th of April is a Wednesday. Okay, it'll be from 6 to about 10 o'clock. So you have to burn one whole evening. That will be during week 13 when things are getting really scary for a lot of students because it's coming close to finals. Okay, so please put that on your calendar. And then I think somewhere around recess week or later than that, I want to have project proposals from all of you. Okay, your project proposals are basically one paragraph about the data set that you're going to use, and then any particularities that you think we need to know about. Okay, those will be publicly described. They will also go on the website, the iSteps website. Okay, so you can see last year we had some projects. Again, you saw some of the pictures of these, but basically you'll have to write a paragraph or two that describes your project, so something like this. Okay, so using faces for attendance taking in class. So you take a bunch of pictures and then you send it to the image classifier. You have to do identification. So this is some type of biometric project. Okay. So our goal today is for everyone to fill this grid out. Okay, so please access it again. It is at this location, 6101 lecture choice at bit.ly. Okay, and then we're going to go through the rest of today for the next 40 minutes with all of your help going through the materials that Jeremy presented for the first 2 weeks. Let's first have a show of hands, or even on Slack, if anyone had problems setting up an environment to actually run a GPU and to do Python notebooks. Everyone was able to do that? You all have access? Okay, Giancan says so. Everyone else? Okay. So you guys all have access to a GPU and can make use of that? Were you able to install the Fast.AI library? Okay. Anyone had problems?
So we didn't have time to finish that. We just got to notice that yesterday, so I'm still sitting.
Okay, yeah, no worries. Hopefully by next week, Friday, we can make sure everyone is on the same page, all try the same exercises. Even though I'm leading the course, I haven't had a chance to do it yet, so I'm behind most of you guys. Okay, so yeah. Anyone else besides, sorry? Sivan, yeah, Sylvan. Everyone else have access and it's able to run Jupyter Notebook? Okay, great. So you're able to try it out. Okay, so a couple things that happened in his lecture. I think he described what image kernels are. So I think maybe you saw this link that he put up in the website, and so I want to discuss this a little bit more. What is going on? Okay, so he mentioned a couple papers as well, but let's first go over what an image kernel does. Okay, so if you have basically RGB image, which is like this one here, it's just a raster of numbers, right? And usually you have the raster of numbers in 3 color channels, right? R, G, and B. So you have 3 separate planes, okay? But here, this one is in grayscale. There's the seed up here, okay? Then what will happen is you have numbers that indicate some information, like the low numbers here are obviously closer to black. The high numbers here are obviously closer to white, okay? And then he describes basically using a kernel to do some type of convolution operation, right? So 3 by 3 kernel just means the size of the kernel is 3 by 3 pixels centered at the middle pixel, and then you have a particular operation you want to do on it. Now, note this is not a normal convolution. A convolution would actually flip around the transpose of the matrix. So it's actually just doing element by element multiplication, right? So if you want to take this sharpened kernel and apply it to, let's say, any one of these pixels, like this one here that says 117, then you would basically multiply the pixels around that 3 by 3 block, right? So over here you can see, if we look at this 117 here, okay, this 117, there's a 74 to the upper left, 127 to the lower right, and so we would multiply both of those numbers by 0 because they're indicated here, right? And then the 117 in the middle by 5, okay? And we do this, and what we would end up is creating another matrix of the same size, right? And you can see this here. So let me pick one of those again. Okay, maybe it was this one, I think. Yeah, and so you can see by multiplying all of those numbers together and then summing them, so it's a linear operation, then you get 148 as the output, and that would be output on the rightmost image, right? So you get the value 148, which is the value of that red cell on the right part of the image, okay? So this is the sharpen operation. You see this all the time in Adobe Photoshop. There are different kernels that you can use, right? I moved the mouse over here. So there are lots of different things you can do. You can blur. You can imagine what type of thing blurring does, right? So it basically is multiplying them with a smoothing operation, right? So all of the multiplications are with small amounts. So you're basically spreading out the image over a larger period, right? Okay. So you can see how that's working, okay? And you can see what it's doing here too, right? Just smoothing out that image. So this is an interesting site to play with because then you can get an idea of what's going on here. Again, you can see that in certain cases, if you set the image kernel in a certain way, you can get edges and corners out, and that's very important. As you saw later on in the lecture, he talks about the image detectors building up blocks, right, through the different hidden layers to different types of detectors. Right, so let's see. Does anyone have the paper link where they discuss the CNNs? I've forgotten where it is. The ones that were in the paper that were shown. This is also meant to be an interactive discussion. So you guys have any questions about ResNet or any of the ImageNet things that have come out so far?
So I'm thinking that all the examples are focusing in the image recognition. Is the same convolution idea being applied to other applications?
Yeah, it's
Text
being applied
examples?
to a lot. Yeah, and I guess we can go around the room if you guys know of other places where CNNs have been applied. Certainly, they make a lot of sense for images because basically, when you do a convolution, you're taking a patch of a matrix and applying a convolution to it, or a convolution-like operation. But it has been used, for example, I think you mentioned text, right? Do you want to say more about it?
So, I have only used the convolution for image classification so far.
Mm-hmm. But it has been applied to text. Can you say more about it, Animesh? Maybe you want to say anything?
One of the classic paper for sentence classification called Kim. It is basically only Kim. There's an author. This paper uses convolution for sentence classification, and by far it's better baseline than other content models like RNN as well. And you can think of similar to image classification. Sentence classification can be thought of dependent on few words rather than sentence as well. So when we want to classify this a sentence, usually we just are looking into a particular spike in the signal where some particular words appear, right? Same applies to when I say sentence classification, it's the superset of all different classes, all different classification tasks, which can be narrowed down to sentence classification. For example, sentiment analysis. So you can say there are three types of sentence here. Low sentiment is sentence like negative sentiment, and then some positive sentiment statements, and then neutral sentiment statement. So any task which can be narrowed down to sentence classification, CNN has shown to give good, uh, better improvement in many complex models, just because those tasks can be seen equivalent to image classification, where we are not worrying about the whole that much as we are worrying about certain spike in the signal. Yeah.
Does that make sense to everyone? So Animesh is saying when you're doing sentence classification, especially let's say for sentiment analysis, not all the words matter, right? There are only certain words that contain very useful information, like you can see the ones here, right? So there might be some words that connote a sentiment, and there might be other words that can flip the polarity, like you have a negation operation, right? Not or something like that. And CNN can do that fairly well compared to maybe a sequence-based classification like an RNN. But RNNs are also used quite a lot for this type of work.
Performs better than RNE.
For this task, yes.
Why? But in for sequences, RNN has a bad performance, right?
Where you need a sequence information later as well. So that means sequence to sequence tasks. For example, translation. For example, direction. So it depends on how you model the task. If you're modeling the task only as classification, you probably don't need to retain the sequence information very well. It would help definitely, but convolution with big enough kernel can take care of a smaller context of sequence as well. So, but just doing classification, complex sequential model might not be.
But for seeing how you the input of the sentence, right? For RNN, you can just input every word into the RNN.
Yeah, that's representation where we say that in each time step one word is going. When you see the model, it's essentially a matrix. So even in RNN or CNN, it's the same matrix. The only difference is that same operation occur for a subsequently smaller part of the big matrix. That we say is time step or sequential model. But essentially, if you see on a big scale, RNN and CNN, they are both a big matrix of input, where same operation is executed on the smaller subpart of the big matrix. It's not that we draw that it's happening one word by word, but if you see a big matrix, what we are doing is we are applying same operation on slice of a big matrix, which you can do with CNN.
So I think later in the course they'll have more to say about RNNs, right? So we use RNNs many times when the sequence of information is important, and we use sequence-to-sequence decoding, right? If you want to get out a sequence instead of a single classification as output, right? So there's an important distinction there. Other questions?
Also, one small point. Classically, for all these traditional sentence classification tasks, we always used to have really few data points. So RNN model required relatively more data points than same size for any model with more direction. For that purpose as well, in traditional sentence classification tasks, same has should have much content.
Okay, so to just summarize that, basically NMS is saying that when you have a model that requires a lot of parameter settings, then you need more data, right? So the CNN classifier, because it has a lot of wait time, right, it's basically using the same set of weights for all of the different convolution operations within a single filter, then you only have to set one large W matrix, whereas in the RNN, you have more problems with time steps. Okay. So in this case, it can be more useful for classification or any type of multi-class classification when you have a softmax at the top. Then you may want to use a CNN as a first baseline because it has fewer parameters to train and it gives you a good baseline. Other discussions? You guys have anything to say about the learning rate? He discusses the learning rate in a little bit of detail in the lecture. You guys don't have any questions or concerns? So the Fast.AI library is using its own optimizer. You said it's built on top of Atom. Any questions that you guys want to bring up?
I'm not exactly sure on why different learning rates were used for the earlier layers and the later layers. Can't we use some sort of an intermediate and for all of it? Probably I missed that. I'm not exactly sure.
Okay, so why do we have a problem with using a single learning rate for all of the layers? Can we guys throw it out to everyone? So do you guys know of the problem of vanishing gradients and exploding gradients in training? If not, let's try to see whether we can bring that up. Give me a minute here. Okay. Get it up. A minute here, sorry. It's not the right link. I do this. I want to show from this computer. I don't think I have it on that laptop. Maybe we can find another way to do it. Okay, so I guess it helps to start here, okay? So when you have a deep neural network, right, with several or multi hidden layers, right, you get your final output over here, right? So you have the softmax that's telling you which of the several classes that you have. And in some cases, you also have the use of, before, sigmoid function for neural nets, right? So the sigmoid function looks like this, right? And so basically the only use of any of these nonlinearities is basically to map negative infinity and positive infinity into the unit interval, right? Because we want to be able to squash it into a probabilistic formulation, right? Between 1 and negative 1 and 0, or in the tan h, from 1 to negative 1. So what happens is when you are doing the output layer and you have an error, you calculate the loss. Then when you take the gradient of that loss, you are going to compute amount to fix the first hidden layer for, right? You're just going to say, okay, maybe it needs to be changed a little bit, okay? And the problem here lies when you use something like a sigmoid function. When you calculate successive gradients farther and farther into the neural network, you're going to get more towards the extreme, to either the negative infinity or the positive infinity end, right? And what that means is that once you get to hidden layers 2 or 1, or all the way back to the first layer of your network, basically the gradients are almost flat, right? And when that happens, even if you have a particular learning rate, you get almost no learning done. So we've seen this being fixed in part using the ReLU, right, as a nonlinear unit, so that we don't have to stick things between 1 and negative 1 or 1 and 0. But that's only part of the reason why we have to set the learning rate at different amounts for different levels. So anyone else want to add in?
I don't know whether my understanding is correct. My understanding is that because we are sort of like doing a transfer learning, we are not doing a model completely from scratch. We have already some modeling training parameters we've taken from somewhere, and then we want to learn mostly in the further layer, deep layer. In initial layers, we just want to some minor tuning, so that's why a smaller learning rate may be more appropriate for the initial stages. Is this my understanding?
I think we want a good learning rate for all of the different levels. And the problem with both exploding and vanishing gradients is that when we see that we have good gradients towards the end of the network, these layers can learn fast. But when we propagate the errors farther down the hidden layers, many times the gradients flatten out. And that means the layers closer to the front of the neural network don't learn very well, right? Yeah. But yes, I think you're partially correct to say that maybe you don't want to make too many adjustments to the beginning layers of the network, because you don't want your primitive detectors to change too much, right? You're suggesting that maybe that the primitive layers should stay more stable, so that the more deeper levels of the network can change to accommodate better feature detection.
Yeah, in the lecture it was kind of close to what he said. Yeah, this, your explanation kind of makes it clearer.
Okay. But I appreciate if everyone in the class can weigh in. I mean, this is a discussion group. It's not a lecture. Okay. Even though I'm a lecturer, that doesn't mean in this case I'm trying to lecture. I would rather you guys discuss as a group. So if anyone has something to say, please say it.
So in case of image classification, the percentage is a representative factor that the beginning, that means the beginning layers identify simple features like curves and lines, whereas the later layers identify complex features like even the images of cats and dogs. So that's why they keep different learning rate for different layers. Even a small learning rate for first layer and high learning rates for the later layers. That factor, the percentage factor.
Yeah, so I think we can go get that particular paper. Let's see whether we can find it. So I'll throw this on Slack. So hopefully next time we'll have somebody managing Slack and somebody leading. You can take a look at this paper. This is basically the same paper that they described in the lecture. And sometimes I think it's generally quite helpful if you go back to the sources, because they will present the math that's glossed over in the lecture. Oh, my network is slow. Well, probably it's because it's casting too. So maybe you've already gotten the paper, I don't know. But we'll take a minute for it to load. Other questions? So I think Jeremy's philosophy in teaching the course is you should be spending less time on the math and more time tinkering, because the tinkering will give you the experiential knowledge that when you go back and get the math, it will start to make sense. This is the what I like to call the business school mentality, which is to say that you only get admitted to business school only after you've been in industry for 3 or 4 years, because business schools find it that if they teach you things, it doesn't make any relation or sense to you until you've had practical experience of doing it all wrong. Okay, so the whole point of going to business school is after you've tried something and you know it's not quite right, then you go back to business school and you optimize it by having lessons. So I think that's his purpose in teaching this course, is just go try it first, okay? Make some tinkering, you break things, make it not work, figure out what some patterns are, and then go and get the math knowledge to figure out why it is that way, rather than get the math first and not have an intuitive understanding for what the parameters are values and their loss functions and the values of those loss functions are trying to tell you. Okay, both approaches work. In academia, we tend to go the other route, like he said. You know, I think there was one part where they were denigrating some machine learning person for saying you should have all the math background first. I think that's a valid approach, but I think there's value in both ways, and I think as PhD students, you should be triangulating, you know, using both directions. Why not? Because you are full-time researchers. You have all the time in the world, supposedly, to do that type of work. Okay, so yeah, this archive paper is taking a very long time to load, but it's loading. So if you find blog sites or things that you're looking on that you think are useful to share them, okay? Put them on Slack. I see a lot of open laptops looking at other things, which is great, but then please curate what you're able to Google and find, put them on the website so that everyone else can have a benefit from that, okay? Again, this is a study group, meaning that we all look together at things rather than each go our separate ways and in our own little cubicles with our own headphones, watch the YouTube videos and never know anyone else exists. Okay. Other things that you guys want to bring up? So in the previous 6101 classes, what we did was we actually did actually ask people to do the lecture in class, but I don't think that's very effective either. So in a flipped classroom, it requires more of a discussion and camaraderie among us to talk, not be afraid to talk and not be afraid to be wrong, and for it to be recorded, it's not a big deal. And then use that to improve our basis of understanding. Okay, so this is the paper that those pictures were taken from. Right, I see some of you have those on your screen too. Right, so as Jeremy was saying, here are the layer 1 types of kernels that are coming out from that. They're basically very simple detectors looking at edges and specific color patches. And I think in this particular data set, they're all natural images, which is why I think Jeremy asked you guys to try different images that are natural images, because the data set that the model is importing from or getting retuned is basically a natural data set. Right? And so you can see things like green patches, different types of greens, different types of what he called sunset colors, right? And edge detectors. And after a couple layers, let's say after layer 3, you can see it's starting to get interesting in terms of what types of things it's looking for. It's looking for certain textures. So these are the image kernels themselves, right? These are images that are maximally activated by those image kernels. Right, so this is looking for some type of intersection of straight lines, and you can see what it corresponds to here. These are some, ovoid patterns which end up looking like car wheels, etc., that are coming out of that. And those are all based off of this image features at previous levels, right? Jeremy also briefly discusses the universal representation theorem to say that neural networks can learn any type of function. Do you guys want to discuss that at all? Yes? No? Don't care? You're PhD students, come on. Or even undergraduate students. I expect undergraduates to speak even more than PhD students in some cases.
I think it's universal representation. Universal approximation.
Approximation theorem, thank you. So what does that theorem say?
It says that, just says that you only need one layer and one activation layer to approximate any function.
Yeah, that's right. We only need one layer. So why do we bother going to so many layers? Like if you see the architectures that are now very prevalent in computer vision, they have hundreds of layers, if not more, right? So if you can use one layer to get them all, why would you use hundreds of layers? What's the benefit of using additional layers?
Or like a combination of different features.
Mm-hmm. Can you say more about that?
Each of the neuron in the hidden layer can actually capture some of the features as you design.
Mm-hmm.
One advantage of using CNN is using a pooling layer and then extract or centralize all the features and then use a combination of different features to achieve better performance.
Okay, so there's a exponentially large benefit in using more layers, right? Because each layer, you can take the output of each layer and funnel it into the next one. So you're building this representation instead of having layer 1 try to learn something like, I don't know, like what we have at layer 7, right? Because that would be pretty hard for a single layer to learn something like that. It is possible, right? You just need enough inputs and enough training data to do that, right? But because you're sharing all of the parameters from the previous level, you have these detectors that are shared, then you can array these, as Shenhao said, using max pooling to achieve resolution independence, right? Because pooling basically changes the resolution of the detector, right? From a small 3x3 or 5x5 image patch to something much larger than that, right? And be able to build on top of these to get more intricate structures, right? So there's another reason why we use multiple layers. Can anyone relate that to dropout? And I don't think Jeremy discussed dropout at all at this point, but if you guys know about dropout, maybe you can say a little bit about why having a hierarchical structure of multiple levels dropout is more effective. We can just save that for another lecture when we get to dropout.
First, when you have for example, when you have a silicon of a very large size, many layers, and each layer it's possible that this neural network will be focusing on concentrating on the training data you're providing. Which means if you divide your data set into 2 or 3 different parts, one is training, one is test, or maybe a cross-validation set. Possible that the neural network is so focused on the training data that when you are feeding your test data into the network, it can actually give you very poor performance simply because the network hasn't seen the data. So then this concept of dropout is introduced. So basically, we'll be introducing a percentage of neurons, and in each of the layer, this percentage of the neuron will be randomly selected and then drop out of the neural network. So even your training data are kept the same as previously, but now because you are randomly dropping some of the neurons, your network will not be solely dependent on the training data. So we can actually give you better performance when you feeding on seeing test data.
Okay, so Shenhao is explaining what dropout is in general, right? So the idea of dropout is to randomly kill neurons during the training process so that you reduce overfitting. Is everyone comfortable with the term overfitting? It's perfectly fine if you're not. Okay, so when we do neural networks, they have a very good capacity to overtune. So we need to keep them from over specifying, and then dropout helps for that. Dropout is exponentially more effective when you have deep neural networks. And that's because when you drop out, you're actually training many different versions of your neural network, exponentially many, because of the way dropout works, because that same neuron dropped out is being cascaded onto multiple upper level networks. And so that's a very big, a good reason. And I think it's explained much more in the deep learning book, the free deep learning network book that's online from, I forgot their names. Benjio is one of the authors, right? Yeah. Yeah. So Goodfellow's book. Yeah, Goodfellow et al. So that's a really good book. But if you read into some of the math details, they give a very intuitive explanation for why dropout is incredibly successful and incredibly useful for tuning deep neural networks not to overfit. Yeah. Okay. Any other questions that you guys want to discuss?
So
Yes.
given all the different types of activation layers that you have, sigmoid, tan, what is the advantage of each one? Or like, how do you choose?
Sorry.
How do you choose which one to use when?
Just try it.
So I think, and again, those of you who have some experience will be able to say better than me, because I am fairly far removed from actually doing experiments. The current advice is to always use ReLU as a start, because it is really simple. Yeah, I think part of it addresses the vanishing and exploding gradient problem, as we had sort of hinted at, that happens with sigmoid and tanh. But it's also that those two other functions are actually not very easy to compute, right? They do require exponentials or other things. So they're expensive. ReLU is like a no-brainer. It's almost crazy that it actually has a name. This is such a simple function, right? Max of 0 and x. There's no reason not to try something that simple, right? Basically, just kill off all of the negative numbers, to zero them out, and then let the positive gradient flow all the way through the network. Yeah. So there are other formulations. There's leaky ReLU and other things like that that allow you to get back the negative domain, but they're not as widely used. I think, like a lot of other things, you can do it in a more principled way and use a better nonlinearity. But the problem there is that the computation cycles you use to do that may not be as effective as adding yet another layer, for example. So the time savings you would get for using ReLU may be more worth it to introduce more model complexity rather than fiddle with the nonlinearity function. But if you guys have anything to say, especially Animesh and Jeffro or Joel, Joel's not here anymore, but if you guys have something you want to add.
Damage or sigmoid is mostly used when you want your hidden layer representation to sum to a unit vector, because in many cases, like for example, some of the interveners function for RNN, it requires the activation to sum to 1. So in those cases, you may probably want sigmoid or damage activation, because ReLU doesn't give any surety that activation of any hidden unit be under some value, I mean, within some range. You want, if you are doing speech processing and you are using a unit vector to bring speaker or something, and you want that representation to be constant so that you maybe later you can plot it in a space, or you want to use word embedding and you use at some layer to plot it in some space. You want to use for many different purposes where you want your representation to be a vector or normalized vector. You can use something like this, because it will always guarantee that your activation for each of them you want to be 0 to 1 or -1 to 1. So you can use non-linearities which guarantees upper bound and lower bound for your intermediate.
So those are also really helpful when you have to build a partition function, right? Something that's normalizing over all of the cases, right? So there's a lot of times that we want to normalize the entire function to sum up to 1, or for it to represent a probabilistic value. Then there you would want to make sure that every factor has a certain bound or a certain sum, so that you can build the partition function, usually 1 over z, right? You see written.
So also the how computationally expensive activation function is in practical use cases. So when I worked at Carousel, we wanted to iterate fast, so we trained our model only for 2 days before we deploy. And when we switch from NH to switch, which is like a new function that came up, we could run it for about 100,000 miles and the loss was a lot lower.
Thanks.
Also from my experience, one reason why ReLU works so well, because it actually drops out all the negative gradient. So it's kind of act like a dropout. So generalize.
One final question about dropouts. I'm just curious to know that, because dropout includes some randomness, right? And you specify how much you want to drop out every single layer. You can control that.
Yes.
You cannot control which neuron that you are actually dropping. Let's say I'm running the model for 5 times, and every time I get some improvement. Maybe the first time I'm randomly using some neuron. Can I actually control, or is that a way that people think controlling which neuron to drop out helps?
You can drop out specific neurons, but I think that's the beauty of dropout, is that you don't, right? You just let the the random system choose. There's a lot to say for randomness. I mean, in computer science, we like random because an adversary cannot pick out examples that make it, crucify your algorithm to do things wrong. But I think in certain model architectures, let's say capsule networks or other things of that sort, which Hinton has introduced, there are reasons why you would want to drop out certain parts of your network and not others, right, if they have semantic meaning. But in the standard CNN or RNN architecture, it's very generic, right? All of the architectures looks the same. When your architecture becomes more complex, you have certain subparts of your network connected together, not connected to other parts. And I forgot what it was, like inception. There's some other model architectures that are used in Vision a lot. They have certain sub-networks, and if you drop parts of those networks, they may work better or not. Yeah, so in those cases, yes, maybe you want to constrain your dropout to certain parts. But I think the beauty of dropout, as it's described, is it's just, you can run it independently, and that you're randomly dropping out nodes. Yeah, including input nodes, right? So you can drop out input nodes that has the ability to do something that's very commonplace in another type of learning algorithm, the random forest. So random forest does what people call feature projection, which is to say, instead of using the whole feature vector, just use a subpart of it, right? So when you do dropout on the input layer, you're basically effectively saying that certain parts of the input you don't get to see anymore, right? For certain, in training, certain parts of the network don't get to see that. So I don't know whether that particularly answers your question, but I think it's by design that we want it to be random. Okay, so it's 11 already. So we're going to stop today's course. So between now and next week, I will assign people to weeks, and then we are going to use the discussion forum here. So for example, week 3 prep, which is already to this week. So week 4, those of you assigned to week 4 are going to need to use this channel to talk to each other, decide what materials you want to cover. Again, it's good if you don't choose too many questions to discuss. I choose too little questions today to discuss, but I think this way we can try to, again, just have people talk. I would rather we talk. It's not meant to be a classroom setting, okay? So once I've allocated you to a session, please join that particular week's preparation channel, say hi, meet in person if you can, because I think it's much better if you know who you are instead of, oh, you're that handle, I've never seen you before, right? Because the Slack gravatars are utterly useless. You would never know that's this gentleman sitting over there, right? Okay, so please help us out by joining the appropriate Slack channel, and again, talking on the project channel to decide what type of project you want to execute for your semester's course, okay? So even if you're a guest in this course and you're not officially in this course as a PhD first-year student, we, again, require you to do the same level of interaction, do the Slack preparation, take charge of 1 or 2 weeks of courses, and do a project. It's the best way to learn. I will also try to do my own project if I can handle my load. Okay, so thank you all for coming. I'll see you guys next week, same time here. Okay, thank you.
Thank you.
The presentation must be
You could online present, but it's much easier if you're here. Yeah. Then maybe you should do a session outside of Chinese New Year.